So, thank you very much, Gretchen. It's a great pleasure, as always, to be visiting the JQI, and I'm really looking forward to many interesting discussions over the next couple of days. This morning, I'd like to tell you a little bit about some of the things that we've been doing recently on dissipative dynamics and optical lattice systems, and in particular, how this is related to our understanding of how heating works in optical lattice systems. And this turns out to be not only something that's very important to understand on a practical level in the experiments, but it also turns out to involve some relatively fundamental understanding and learning about many-body quantum dynamics. In particular, understanding how to really describe, dissipative processes in the many-body systems, and then also to think about how the many-body dynamics works in terms of if you have heating processes, if you have spontaneous emissions, or other things going on in the system, whether the system is able to thermalize the energy that gets put into it over some period of time. And so this involves sort of some combination of understanding dissipative many-body dynamics and understanding also many-body dynamics in a closed quantum system as it tries to thermalize that energy. I'll say more later, but a lot of the work I'm going to present today has been done by a combination of various people in our group in Pittsburgh. So Shavik Sarkar, who's a graduate student there, Johannes Schachermeier is a graduate student who recently moved as a postdoc to Jilla. Stefan Lange is a postdoc in the group, and also we had very interesting collaborations on these things with Loda Pollitt and with Matthias Treuer. As Gretchen mentioned a moment ago, I'm sort of in a superposition state at the moment. I think it's relatively classical, but I am partly in Pittsburgh and partly at the University of Strathclyde in Glasgow. And sort of over the course of the next sort of half a year, I'm sort of going to be doing that quite often. And sort of then after that, from the middle of next year, my group will move to the University of Strathclyde in Glasgow, but I'm still looking forward to keeping in touch with everyone over this side of the Atlantic. So the background to the things that we do is something that is probably very well known here at the JQI. There's been an enormous amount of interest in the last 15 years or so in taking degenerate boson Fermi gases where we have very good microscopic control in experiments and also good microscopic understanding in theory of the interactions and of the motion of these atoms, and loading them into optical lattices in order to realize strongly interacting lattice models of the type that people more often discussed previously in solid-state physics. And so with bosonic atoms or with fermionic atoms of multiple species, you can realize models like the Bose-Hubbard model and the original fermionic Hubbard model, where you have tunneling of particles between neighboring sites, and to a good approximation, you simply have a description in terms of that and the interactions when two or more particles sit on the same site. And what's very nice and what has generated a lot of interest in experiments around the world is that you can realize these models again with very good microscopic control over the parameters and a very good microscopic understanding of the approximations that go into making this the microscopic description. And then you can use this as a way of studying the thermodynamics of the system, interesting quantum phases that come out at low temperatures. And you can use this maybe to simulate a range of physics that might not be easy to realize in other systems, or maybe you can use this to solve models like, say, a 2D Fermi-Hubbard model that may be difficult to solve theoretically. So this has motivated a lot of the experiments, but of course there's a lot more to these systems and their capabilities than just thinking about thermodynamics in these lattice models. In particular, these are ideal systems to think about out of equilibrium dynamics. So firstly, we have very good time-dependent control because the dynamics, the tunneling in these systems typically is of the order of millisecond timescales, and that allows you to vary the system parameters very rapidly, so the depth of the lattice, effectively the tunneling parameters and the interactions on a timescale that is fast compared with those dynamics. And this allows you, for example, to perform quantum quenches and then, for example, track what the system does in time. Think about how it responds if you suddenly change a parameter, and then ask, for example, fundamental questions like, if we suddenly change a parameter and the system goes far out of equilibrium, under what conditions might it settle back into an equilibrium that looks like a thermal state? So under what conditions does the system thermalize after a quantum quench? What happens in the meantime in the dynamics? To what extent do you see, for example, entanglement growth in the system in space? Okay? To what extent do particles on one side become entangled with the particles on the other side as a function of time? So you can start studying a lot of very fundamental questions in that sense. At the same time, out of equilibrium dynamics, manipulating the system as a function of time gives you a set of tools to do things like to prepare states in the experiment. So for example, you can think about adiabatic state preparation. If you want to make very low entropy states that are complicated, for example, states with magnetic order in a two-species model with fermions or bosons, you can, for example, try to start in a state that is maybe easier to prepare with lower entropy, perhaps because it's a band insulator state that has a large gap to excited states. And then, by manipulating the lattice potential, go over to regimes where you have sort of magnetic order or states that are typically fragile, they require low entropy. If you can start with low entropy and then manipulate the lattice adiabatically so that the entropy doesn't increase, it gives you, in principle, a new tool to prepare states. So that is non-equilibrium dynamics can be of fundamental interest and also can be used as a practical tool. So there's a particular type of non-equilibrium dynamics that has interested us in the last few years, and that's non-equilibrium dissipative dynamics. And this is where these systems sort of start to couple back to their, if you like, quantum optics and atomic physics roots. Because when you talk about dissipative dynamics, when you have some quantum system that is coupled to a much larger environment, in most systems, this creates something that is very messy to describe theoretically and can be often essentially an unwanted complication. If I have, for example, some sort of qubit in the solid state system, and it's say a spin qubit of some description, the last thing I want it to do is start talking to the spins that are in the medium around it. And I know that these dynamics can often be complicated. They can often be non-Markovian. Often you have couplings that are stronger than you would like them to be. And you always have difficulties because the sorts of energy scales that you're exchanging, sort of the difference in energies between your different spins, tend to be of the same sort of energy and frequency scales as the other energy and frequency scales that you're dealing with in the problem, the things you actually want to see, say, in quantum dynamics of your spins. The nice thing in atomic physics and quantum optics is that you can go into quite a different parameter regime for the system-environment coupling. Namely, if I think about something simple, like a two-level atom with a ground state and an excited state, and I think about the most obvious type of dissipation here, which is if I prepare the atom in an excited state, then it can spontaneously emit a photon and decay to the ground state. Then I suddenly have a situation where I can have a very large separation of my energy and frequency scales. In particular, if you look at the types of frequency scales with which you normally drive the transition between the ground states and the excited states with lasers, and you look at the typical decay lifetimes of the excited states, these tend to be parameters that are in the maybe tens of megahertz for the decay, maybe for the effective Rabi frequencies, gigahertz or tens or hundreds of gigahertz. But the frequency of the photon that you emit is much larger than that. That's 10 to the 14, 10 to the 15 hertz. It's a very, very large frequency scale compared with all of the other energy and frequency scales that you're dealing with in the problem. And this suddenly makes atomic physics systems very nice to deal with in terms of making a microscopic description of those dissipative dynamics. Because you can make a whole lot of approximations. You can make the approximation that this is essentially Markovian, that this photon runs away, and that the environment doesn't remember what has happened in its previous interactions with the system. You can make the assumption that this coupling is weak because, again, the decay lifetime is much smaller a frequency than the frequency of the photon that's being spontaneously emitted. So weak coupling approximations work, so Born approximations, Markov approximations work, and there are a whole lot of theoretical formalisms that come out of this where we have master equations and quantum stochastic Schrödinger equations that allow us to describe dissipative processes really for an open quantum system on a microscopic level, going back to a simple equation for the density matrix of the system. Really allows us to form a closed set of equations. And then we can start thinking about the dynamics of this properly. We can ask, what is the effect of the coupling to the environment on the state of the system? If we know something about the environment, what can we infer about the state of the system? So feedback and so on and so forth. And then you can go further, and we know that in atomic physics, people have used dissipative techniques to produce laser cooling and optical pumping and methods to essentially very substantially reduce the entropy of the system. So suddenly, dissipative processes are something that we can describe and something that can even be used as a tool. And the nice thing is that with many body systems with cold atoms and optical lattices, you now have really a quantum optics, atomic physics-based system where you have a many-body system that now has a series of types of dissipation that you can understand theoretically and that you can really control. So with cold atoms and optical lattices, we can think about dissipation in a whole lot of different contexts. You can think, for example, about adding dissipation directly in a way that you would like to have it. You can, for example, add a reservoir gas to the system that can be used to cool atoms that are in higher bands of the optical lattice down to the lowest band. And you can start thinking about this like a system where the excited band is like the excited state in your two-level atom, and the lowest band is like the ground state, and the large frequency scale that's larger than all of the other dynamical scales in the problem is the separation between the block bands, which is normally much, much larger in energy scale than anything that goes on for the normal dynamics within one band. You can also think about, for example, the dissipative effects of having lost processes in the lattice, which are again normally unwanted, but you have a nice description for the dissipation because the energy released in, say, a three-body loss event is normally on a scale which is many orders of magnitude larger than the energy scales for the atoms that are moving in the lattice. These things are lost, they run away quickly, you can make Markov approximations and see that in fact you can have things like a continuous quantum Zeno effect where three-body loss prevents three-body occupations and gives rise to effective interactions that you can actually make use of. You can also go further. You can think about using these things for driving systems into interesting many-body states, for example, using complicated schemes with group 2 atoms and induce spontaneous emissions. You can even think of ways that you might generate pairing between fermionic species in some pattern, really by directly controlling, again, the dissipation for atoms in an optical lattice. So that is to say, dissipative processes, even things that we don't like, could turn out to be useful. There's, of course, another set of dissipative processes that people just try to avoid, but that are becoming more and more important to properly understand in these experiments, though. And that is essentially dissipative processes associated with heating in optical lattice experiments. And it's becoming more and more important to really understand how to characterize and control heating in these experiments. And it's that side of dissipative dynamics that I would like to focus on primarily in the rest of the talk today. So why is this becoming so important? Well, it's becoming so important because there's a lot of interesting physics that people are interested in seeing in these optical lattice systems. We know that people have investigated low energy states in a Bose-Hubbard model where you have a transition as a function of the ratio of the interaction strength to the tunneling between sort of superfluid states where the particles are delocalized across the lattice and mod-insulator states where they're exponentially localized. And people have seen this, characterized it, and compared it very nicely to theoretical calculations. But if you go to slightly more complicated systems, for example, fermionic species in an optical lattice, people are very interested in initially trying to see magnetic order here, which is induced by processes where you can essentially lower the energy. So if you have much stronger interactions than tunneling, the particles again want to arrange themselves if you're at half filling, so one particle per site, where you have really particles exponentially localized at particular sites. But then they can lower their energy via virtual processes where they tunnel and tunnel back. And if they arrange themselves so that they have an antiferromagnetic order, then you can see how they can lower their energy in second-order perturbation theory by doing that, whereas if you have particles of the same spin sitting next to each other, they can't. And so you generate this type of Néel order, actually with an effective Heisenberg Hamiltonian. And of course, people talk about maybe going over and seeing if this model in 2 dimensions contains pairing and superconductivity if you go away from half filling. But in order to do this, you have to get down to sufficiently low temperatures because these sorts of energy scales, which you need even for the Néel order, are very small. And at the moment, although there's been some very nice experiments in the last year where people have seen local antiferromagnetic correlations in these systems, mostly the temperatures for an isotropic lattice like this are estimated to be still a little bit above where this Néel transition is. And so what's become very important is the questions of how to cool to lower temperatures. Maybe you saw some ideas in the last couple of slides that could be useful going forwards in experiments. But also, and very importantly, the characterization and proper control in the experiments of the competing heating processes that, of course, try to force you back up to higher temperatures. So where do these things come from? Well, they come from a variety of different sources in the experiments. You can have, for example, heating due to classical noise if you have laser intensity fluctuations that give rise to fluctuations of the depth of the lattice. And you can have jittering of the lattice potential backwards and forwards. But you can also have spontaneous emission events, which are really intrinsic in this system, because if you generate your optical lattice using laser light, then obviously you do this by coupling off resonantly to an excited state. You always have some probability of having the particle in an excited state, and no matter how far detuned you are, you always have some rate of spontaneous scattering. And it's essentially impossible intrinsically to get rid of that entirely. You can make it a bit smaller, but then there are also limits due to laser power. So, of course, this then leads to a whole set of intrinsic questions in the dynamics. So firstly, how do these sorts of processes heat the atoms in the lattice? Okay? Is there some interplay between the heating and the many-body physics? Do we have some many-body states that are more susceptible to heating than others? Okay? Also, what's the role of thermalization here? If we add energy to the system in a spontaneous emission event, does the system simply redistribute that energy amongst all of the atoms and go to a state that looks like it's simply slightly higher temperature? Or does the system in some way remain out of equilibrium? Can it thermalize the energy that's been put into it on typical experimental timescales? And then in the end, by understanding these things, how different many-body states are affected and whether the system thermalizes, we'd then like to answer essentially a practical question, which is how at the end do you make choices in an experiment to help you control or minimize the heating in those experiments. Okay. So what I'd like to do is I'd like to start off by talking about our description of heating of many-body states of bosons in an optical lattice. And then I'd like to talk about this question of whether or not the system will actually thermalize the energy that's been pumped into it on typical experimental timescales. And then afterwards, I'd like to come back at the end to talk briefly about the heating of many spin-ordered fermions, okay, and how that sort of changes the discussion. Okay, so let's start with the heating of bosons. And again, what we start with is a description for what happens to the system when it couples to a reservoir, which here is the external electromagnetic field, okay? And this is something that is very well known in quantum optics and atomic physics for single particles, but here we're going to look at the same description for a mini-particle system. So the first thing that we do is we go through, we make the approximations that I described before, and we derive a master equation, which to some of you, if you're theorists, you're going to like the look of all the symbols here, but you don't necessarily need to understand everything in this equation to understand the physics that's going on here. So this simply is an equation of motion for the density operator of the atoms in the optical lattice. You have some coherent dynamics, which essentially is the many-body field operator version of the Hamiltonian for the system, that eventually, if you restrict it to the lowest band, will give you back your Bose-Hubbard model. Okay? And then this is in terms of, again, the bosonic field operators, the dissipative part that comes from scattering photons. We have integrated over the different directions in which the photons can be scattered, and at the end of the day, it comes down to dynamics described by a term like this. And this term, which for the experts in the audience, you see is almost diagonal in position, okay, gives rise to two things. Firstly, if I am an atom in an optical lattice and I scatter a photon, I have a recoil momentum that can, in principle, push me up to a higher band. Okay, it can take an atom in the lowest band and it can transfer it to a higher band. However, this is typically suppressed in the sort of deep optical lattices that we have in an experiment. You have a Lamb-Dickey parameter that comes into calculating these rates, which basically is the ratio of the trap length for an atom sitting in the optical lattice to the wavelength of the photons that are being scattered. And if you look at this ratio, then it's about 1/3, or a little bit smaller, for lattices that are about 7 to 10 recoils in depth. And if you look, what happens in the rates of these scattering processes is that the Lamb-Dickey factor squared comes into it. What that means is that only about 1 in every 10 scattering events, roughly, is going to put a particle in the higher band if you start with a typical red-detuned optical lattice. Okay? And so that means that often that you're going to be dominated by these processes that bring you back to the lowest band. So if I just stay in the lowest band, what does it do to the atoms? Well, the main effect then is that by scattering a photon, I give the environment information about where the atom was that scattered the photon. Okay? To think about this physically, you know, if you want to see where something is, you shine light on it, you let it scatter light, and you get information when you see the photons coming off about where that object is. Okay? This is essentially the same thing going on here. If you have a particle that was delocalized across different lattice sites and it scatters photons, it gives the environment information about where it was in the sense of if it was initially in a coherent superposition of being in all of these places, then afterwards it's in a mixture of either being here or here or here or here, assuming I didn't measure the photon and I don't know exactly where it is. Okay, but it tells the environment where it is, so therefore I go from a superposition into a mixed state. And the length scale on which I get this information out, the length scale on which the atoms become localized, is the length scale given by the wavelength of the photons being scattered. And you can see that actually mathematically from the master equation, because this is essentially like a position measurement where the master equation is diagonal, almost diagonal, with some function here of f that depends on x minus y, and the length scale across this rapidly decaying function is given by k, which is, you know, the wave number of the photon, so therefore 2 pi over lambda. I'll come to that in a moment. That's an excellent question. Okay. So what happens is that this photon is localized. Now, whether you use, so the atom is localized by the scattering of the photons. Now, whether you use blue detuned or red detuned, this localization effect will always occur. The difference between blue detuned and red detuned light is only the relative rates of these processes where the particles stay in the lowest band or go to a higher band. Now, if you have a look at that, you really look at the difference between red detuning, where the frequency of the lattice laser is below the frequency of the dominant atomic transition, or blue detuning, where it's above the frequency of the dominant atomic transition. Okay, the difference is simply, for red detuning, the atoms are trapped at the light intensity maxima. It looks to them as though you have essentially almost a homogeneous light field, and then they have both these scattering processes and these scattering processes. What happens for blue detuning is that the atoms are trapped at the light intensity minima. You have fewer spontaneous emission events, and that comes almost entirely from a very strong decrease in the rate of these processes. So in fact, these processes become fourth order in terms of their rate in the Lamb-Dickey parameter, and the dominant scattering events in a blue detuned lattice transfer you to higher bands. And you can see this sort of coming out in the relative rate of scattering events. You see this is the line for red detuned lattices, and this is for blue detuned lattices. We can take initial states of particles in the lowest band in a Bose-Hubbard model, and we see that for blue detuned that the scattering rate is always much smaller, and for red detuned varies a little bit as a function of U over J. That's because up in this area we have higher probability with lower interactions of having multiple atoms on a site. And if you have multiple atoms on a site, you can increase your scattering rate by, depending on the language you want to use, superradiance or Bose enhancement of the scattering. This doesn't happen for blue detuning, because for blue detuning they come back, the atoms that scatter the light, to a different state within the lattice.
Do you need that power supply there because you're tripping over?
Okay. Probably not. I hope not. Okay. The interesting thing is that despite the difference in scattering rate, the actual rate of energy increase is the same for blue detuned and red detuned light, to a very good approximation. So the main reason for this, if you look at this picture, is that the rate of transfer to higher bands is essentially the same in the two cases, and this is the process that dominates this rate of increase of energy. However, even if you account for the fact that you can increase the energy via localizing the particles in position and delocalizing them in momenta, it turns out that you can show really exactly that there are slight changes in these rates of transfer to higher bands in blue and red detuned lattices that add up to this being essentially equal. So does that mean that it doesn't matter whether I have blue or red detuned lattices? Okay. The answer is actually no, it doesn't. And the reason why is this increase in energy is not a sufficient description of what happens to the many-body state. Because typically, the system will not thermalize all of the energy that's pumped into it on typical experimental timescales. If it did, all I would have to do is determine how much energy was going in. But here, I can have processes, for example, where particles are transferred to higher bands, and if they are, and this is of course the dominant process in increasing the energy, then they're in a situation where the separation between bands is much larger than these other energy scales, the U's and the J's in the lowest band. And as a result, it would take a very high order process in perturbation theory to redistribute this band gap energy amongst all of the particles in the lowest band. And as a result, essentially, this doesn't happen on typical experimental timescales. If I have multiple particles in the higher band, they can collide, and one can go higher and one can go lower. But I can never take this band gap energy and redistribute it amongst the particles in the lowest band, which means it doesn't thermalize that band gap energy on typical experimental timescales. So now it's not sufficient just to calculate the rate of increase of energy, and I've got to ask, well, how does the state of atoms in the lowest band actually really change? And this is actually good for experiments, because it means that there's a large extent to which the bulk of the energy that goes in just creates a few impurity atoms that run around in the higher band, but can't transfer all of their energy to atoms in the lowest band. That is, if you estimate how the system is heated by just calculating the energy that gets pumped in, you will, by a very long way, overestimate the heating that you're getting. So actually, it's good news for experiments that it doesn't always thermalize. But so what actually does happen then? How do we describe now the heating of that mini-body state? Well, we've got to solve the master equation properly. Okay? So how do we do that? Well, one way, of course, you can have various perturbation theory approaches, but you can go beyond that then, and you can look at numerical ways to solve that master equation. And what we've done is we've combined time-dependent density matrix renormalization group methods, which essentially, for one-dimensional lattice systems, give you a way of calculating time-dependent dynamics of states, really integrating the mini-body Schrodinger equation. Okay? We've combined that with quantum trajectory methods from quantum optics that essentially, by stochastic sampling of the evolution of pure states, allows you to build up the dynamics of a density matrix. So essentially, we have a stochastic method that, if we can propagate states, will allow us to build up the behavior of a density matrix. And we have a many-body method that, in one dimension, allows us to calculate the propagation of states in time. We combine these two, and this gives us a way, on reasonable timescales for this experiment, of really propagating the master equation in time. So to give you a simple idea as to what comes out of this type of treatment, if you take, for example, hardcore bosons, so very large U over J, we'll do soft core in a moment, and you look at this below unit filling, then what happens over time is that initially the quasi-momentum starts so that if you start with zero temperature, that the atoms are essentially near zero quasi-momentum. And then as they scatter photons, particles are localized in space, which means that they delocalize in quasi-momentum, which means that their kinetic energy, which we're plotting here as a function of time for particular stochastic trajectories, increases. And these jumps here in the stochastic trajectories are essentially associated with scattering photons, delocalizing the atoms. So if you then average over a whole lot of trajectories, you can build up really the average kinetic energy in the system as a function of time. And what you can't quite see here on the plot is that for hardcore bosons, this is analytically solvable. And we have the analytical solution here combined with the numerical calculation with statistical error bars, but you can't see the dashed line because basically they're overlapped. Okay. So we have a numerical method that allows us to do that. And so then we can go beyond just calculating for hardcore bosons. We can take really finite U over J and ask, for example, if we have the single particle density matrix that gives us the correlation functions in the system, how do they change over time as we scatter light? We know that in the Bose-Hubbard model, we expect in the superfluid states that there are long-range off-diagonal correlations, whereas the correlations in the single particle density matrix should decay exponentially as a function of distance in the mod insulator. And in an experiment, this is directly related to the momentum distributions that are measured, where you see the peaks in the momentum distributions from interference of particles coming from different places in the superfluid, and these are washed out with these exponentially decaying correlations in the mod insulator. So you can effectively measure these things directly in the experiment as well. And what we do is we calculate this. We start with a superfluid state at finite U over J, and we see, with including light scattering in the lowest band, how those correlation functions change as a function of time, here averaged over 1,000 trajectories. And you can see really what happens is that the spontaneous emission events are localizing the particles, and this is leading to decay of these off-diagonal correlations. And we can really track that directly in the calculations. And what we understand out of that is the following, that within the lowest band, the most important thing is that the particles are being localized, and this is giving rise to decay of these off-diagonal correlations. That means that a superfluid state is going to be much more strongly affected by spontaneous scattering than a mod insulator is. It will be robust relative to the superfluid. And we also see that the decay is proportional to the rate of localization, which is proportional to the scattering rate, which means for a superfluid state that there's going to be more problems with spontaneous emission in a red detuned lattice than in a blue detuned lattice because there is more scattering. It doesn't matter how much energy is pumped in total, it matters much more for a superfluid state how much scattering there is. Okay. So these are sort of simple conclusions that you can come to from these sorts of calculations. But then we need to go beyond that because we'd then like to ask, well, okay, that's fine. We get a decay of correlations. Does this lead to some thermal state as a function of time? Does the system actually thermalize the energy that you're putting into it? Or is this some sort of out of equilibrium state? So I've already told you that if you transfer particles to a higher band, that you don't get thermalization on experimental timescales. What about with the scattering processes where the particles stay in the lowest band? So in principle, the atoms in the lowest band can thermalize the energy on faster timescales because in the end, this is all just dynamics within one band. And as I'll show you in a moment, there's experimental evidence that you might get thermalization under at least certain experimental conditions. So the question we want to ask is, can the atoms in the lowest band thermalize the energy that is added to the system on the timescale over which the system is being heated? Okay? So we have to study the thermalization essentially that results from what is essentially like a local quantum quench. There have been a few studies in the past of global quantum quenches where you change a parameter and look at how the system responds. What we're doing now is we are localizing a particle that has scattered a photon, and now we're asking essentially, can the atom now delocalize? Can it thermalize the energy that comes in this sort of local quench where something happens just on one side? So what do we expect? Well, we know that for some quantum systems that the system doesn't necessarily thermalize energy that gets put in if you push the system out of equilibrium. So there was this very nice experiment by the group of Dave Weiss at Penn State going back a few years where they had strongly interacting particles in 1D, and they showed that the system, because it was essentially near integrable effectively, does not thermalize, and you end up with momentum distributions that over long time scales are still very far out of equilibrium. However, in the Bose-Hubbard model, we know that for finite U over J, the system is supposed to be, in a sense, non-integrable, and so we might expect it to thermalize. And there were, just a couple of years ago, some nice comparisons of experimental data from Munich as they let a superfluid state in an optical lattice heat due to spontaneous emissions, where they measured as a function of time the momentum distribution in the experiment and then compared it with finite temperature calculations, really equilibrium thermal distributions from quantum Monte Carlo, and they found exceptionally good agreement. So this would seem to give evidence that this system was, in a sense, thermalizing on the experimental timescales. And again, most of this heating really came from light scattering of the sort that we've been talking about. So you might expect a whole lot of different things. The other side of the expectations here, though, is the following, that I said that the Bose-Hubbard model is non-integrable. That's fine, but here we're dealing with a very small local quantum quench. So it could be that it depends very strongly on what the low energy of the spectrum of the Hamiltonian looks like. And so it could be that this also changes as a function of parameters as the structure of the lowest energy states in the Hamiltonian changes. So a priori, I can argue two different ways. I can argue maybe it will thermalize, maybe there's evidence that it does, but maybe I might not expect it to if it's just a local quantum quench. So what we set about to do was ask this type of question in initially the simplest possible way that we could. Okay? We take a system, a closed quantum system, we have a quench where there's a spontaneous emission event for an atom on one particular site, and then we look at how the system evolves in time after the quench. after the quench, obviously, there's some new fixed total mean energy. And then we can look at what happens to, for example, the kinetic energy or to some other generic observable. What we can then do is we can take this energy, which is fixed after the quench, and we can fit a thermal distribution for the same system size. We fit a temperature T so that we get the same mean energy as we get over here. And then we ask if the other observables also fit the thermal distribution with that same temperature. Okay? So what happens when we do that? So again, at time 0, we have a quantum quench, local quantum quench where there's a spontaneous emission. And then we look, for example, at the kinetic energy as a function of time. And this is what happens to our kinetic energy. So here was our ground state kinetic energy. We have a spontaneous emission, it goes up. Then there are some short time dynamics, and then it seems to relax. And it's a little bit gray on this projector, but I think you can see this sort of faint gray line coming across here. And this looks like the asymptotic value of the kinetic energy that this line is going to. But that's not what is plotted. What is plotted is the expected thermal value of the kinetic energy if we have the same mean energy, total energy for the system that I have in this blue line. In other words, the system seems to relax on a short time scale in terms of tunneling time, so about half a dozen tunneling times. It relaxes to the value of kinetic energy that I would expect from a thermal distribution.
What's the thin line that seems to be diverging at short times?
This one here is an exponential fit to this decay.
Oh, I see, okay.
Okay, this is simply an exponential fit. So then over here, we do the same thing, but we start just over the mod insulator side of the superfluid mod insulator transition, which in 1D is at U over J is 3.37 for unit filling. And here you see that the values we calculated from quantum Monte Carlo for the thermal values are very, very different to what this appears to relax to, also on a relatively short time. So there appears to be a short time relaxation, but it goes to something that is very different to the thermal value. And what's interesting is that although the equilibration rate, this rate that we fit with this decaying exponential, appears to undergo a simple crossover. So it's slow for small interactions, it's slow for large interactions, and there's a nice smooth crossover in the middle. And this is all on roughly the same time scale as you go across the transition, which happens at this dashed line here. That if you look at the discrepancy between this initial equilibrium value and the predicted thermal value, it's essentially 0 on the superfluid side of the transition and suddenly goes up here on the mod insulator side of the transition.
Just so I can understand the mod insulator regime, can you tell me how many bands and hardcore and all?
Okay, so this is all a single band. Okay, we're assuming that the spontaneous emission leaves the particle in the lowest band. Okay, this is finite U over J, and everything is at unit filling. Okay. So, and you can see this for different system sizes, it goes up like this. Now, we obviously can't say that for very large systems, there might not be other processes that are much longer timescales take it to something that more closely resembles a thermal state. But what we can clearly say is that there is a short time relaxation on both sides of this transition, and that at the transition point, there is a very strong change in the character of that relaxation, and that this, of course, is what is important in the sense that, that these are the timescales over which these heating events are happening. They're going to be happening in the system on the timescale of, typically every 10J you're going to get depending on the experiment, every 10 to 100J you'll have a spontaneous emission event per particle, which means that if you have 50 particles in your system, then this is the sort of time scale on which one of them in your 1D tubes, if you have a 1D system, might undergo a spontaneous emission event.
So what are the excitations that this localizing process in the lattice layer is leaving behind?
Okay, that's exactly what I'm about to talk about. Obviously in the extreme U over J limit, these are essentially propagating particle hole pairs. Okay, and you can understand why for U over J is 20 or so, why this would not thermalize on short timescales, because you're just going to get ballistic propagation of these particle hole pairs. What was surprising to us is that you see this marked change in behavior also really right at the transition point, where you can't describe these things as simple particle hole pairs, because in 1D, again, this is just U over J is 3.37. Okay, so this cartoon picture of the mod insulator is not really valid in that regime. So let me maybe plot some of the low energy spectra for small systems, and then you'll see a little bit more how that crossover goes.
Now maybe this will become clear, but if I've understood correctly the lower left-hand panel, it says that a bigger system has a bigger discrepancy. Is that right?
Yes, so that's
So
what
should
we're
that just
seeing.
be the naive assumption that, well, anything that happens in a bigger system is going to take longer, or is that more nuanced?
Well, no, I think this is a little bit more nuanced here. One has to be a little bit careful because we're making a single quench on a single site, which means that this is not really scaling properly in terms of the energy that we're putting in with the system size. But what you would expect is that if you look at this, that in principle it should converge to something in a larger system. And what's happening here is because we average over the positions at which these things occur, that there are boundary effects in the smaller system that change those values. And in fact, if we went to larger systems, I would expect it to be very similar to the MS96 result, because this starts changing more and more so. You see here we're always doubling the system size, and I think eventually this will sort of converge to...
That you'll come to this sort of asymptotic discrepancy. The discrepancy won't keep getting bigger as you make the system size bigger. The anomaly is the small system.
Exactly right, yeah. Okay, so one way to try to understand what's happening here and how it might depend on the low energy spectrum is to do the following, where we know that after the spontaneous emission event, we can always expand the state in terms of the eigenstates of the Hamiltonian, and all that happens in a coherent quantum mechanical propagation afterwards is that those eigenstates pick up phases, which means that if we relax to some steady state, then the value of any observable in that steady state has to be essentially a weighted average of the expectation value of the observable in the eigenstates of the Hamiltonian. So let's plot that. Let's take the kinetic energy and let's plot the values of the expectation value of the observable as a function of the energy of the eigenstates. And when we do that, what we see is on the superfluid side here, we're changing U over J. This is a beautiful straight line, and you see now immediately why we get this very nice averaging where it goes down into something that agrees with the thermal average. At the phase transition, this breaks up into a much more complicated low energy excitation spectrum, and then eventually it goes across into a spectrum which is just these particle hole pairs that I was talking about when I answered Ian's question. So here are your particle hole pairs emerging beyond U over J is 10. Let me show you that again. But you see right up to the phase transition point, you get this beautiful linear behavior of the kinetic energy as a function of energy, which is trivial at U over J is 0, but highly non-trivial here. And you can see now again this change in the low energy spectrum, which is essentially what gives rise to this qualitative change in the relaxation behavior. Because we have a local quench, it is very sensitive to the particular structure of the low energy spectrum of the Hamiltonian, and that changes markedly at the quantum phase transition point, and this is why we see this, this strange behavior where you get a change in the relaxation. And if you have a look at the population of these states, this is now the sort of C alpha squared after the spontaneous emission event, and you can see that we populate a variety of states across here, and once you get up to the phase transition point, exactly how you populate those states is going to matter a lot in determining these sorts of values that you get for an observable after relaxation. I should comment we've done similar analysis with the momentum distribution to also look at what happens for really long-range observables rather than just local observables like the kinetic energy, and we find similar sorts of things with nice relaxation in the, on the superfluid side, but something very markedly different as soon as you're on the mod insulator side. It also, within the momentum distribution, if you go to small momenta where you have to look at really long-range correlations, they take longer to thermalize also on the superfluid side than the short-range correlations do. We've also looked at what happens when you have multiple scattering events, and the bottom line is that you could see these things in an experiment because with multiple scattering events you get a bigger signal, but basically the physics remains very similar if you also have multiple scattering events. And so we did this assuming that you had near-resonant light scattering over a short period of time and then shut it off and looked at how the system relaxed. And you got large discrepancies past the superfluid mod-insulator transition, but on the superfluid side, it relaxed down to the thermal values you expected in a few tunneling timescales. There are some very interesting open questions still here. For example, these basic ideas, the sensitivity to the low energy spectrum should generalize to higher dimensions, but exactly how and exactly what the properties are of the spectrum that are going to be relevant is somewhat an open question. We have some ideas to really track the thermalization locally and try to use maybe spatial resolution in experiments to get more information about how this is happening. There are some questions as to what happens with local versus global quenches if you make the global quenches small and just try to populate the low energy spectrum. And we also have been looking at different studies of classical noise and how that leads to heating. The question is what happens with thermalization there. The last sort of comments I'd like to make on this heating are to go back to the interesting case that people are trying to realize in experiments at the moment of spin-ordered fermions. And here is, again, as I said at the beginning, the system here has this interesting energy scale and frequency scale that is very small, a sort of J squared over U perturbative scale. And so even if our spontaneous emission rate was, say, 1/100th of J, which is probably about where you are in a typical far-to-tuned optical lattice now, that's kind of fine if your dynamics are of the order of J. But if you make this J over U, sort of to go into this perturbative limit here, if you make that 1/10, then suddenly your scattering rate is only sort of a tenth, as much as a tenth of your typical dynamical timescale. And so if the spin correlations decay with gamma and your dynamical timescales are almost of the order of the spontaneous emission rate, then you start to get into trouble. And so I think it's a very important question to ask, do the spin correlations themselves decay with the scattering rate like we saw for the correlations in the superfluid state? So of course, in order to think about this, we have to think about the atomic physics, and there's a very simple message which starts to help us already immediately. If you have, of course, a laser that is tuned close to resonance on the excited state, we know that you have chances to flip the internal state of the atom. We know that as a result that you would always expect spin correlations to decay with the scattering rate. However, in a far-tuned optical lattice, we can often be in a much better situation because if you're far-tuned, then it's much harder for the system to flip that internal state. And if you take sort of an extreme example, like you take an alkaline earth atom where you have really your spin degree of freedom encoded on the nuclear spin, it's very clear that this cannot be flipped or is flipped with a tiny probability that depends on the ratio of the detuning to the hyperfine structure up here, the hyperfine splitting here. And so normally on experimental timescales, you're not going to flip or directly decohere the spin due to spontaneous emissions. So if it can't directly flip or decohere the spin, what does it do? Well, for this, we can look at what happens in a double well. We can see that you have a ground state that contains different combinations of up-down and down-up. But as I said before, you also, with probability of the order of J squared over U squared, have these doubly occupied sites from the Fermi-Hubbard model. Now, if you have that, but you have no direct spin decoherence, then what a spontaneous emission does is it basically distinguishes the difference between having no atoms on a site and having one and having two. And so essentially, what are decohered versus each other are states with just single occupation versus states that have double occupation and no occupation. And what that means for the dynamics of spin correlations is that the decoherence in these models is actually suppressed by a factor that basically is the probability of having doubly occupied sites. In other words, you get another factor here in the lowest band of j squared over u squared, which basically means that you bring the rate of decay of the spin correlations back down by that sort of order of magnitude that you'd lost by having small j over u. And this is for a double well. We also did calculations with time-dependent DMRG, and the bottom line is this does scale, again, as the probability of having doubly occupied sites in the system, and you see this real additional robustness here. So that's the main message I wanted to get across. The other thing I wanted to say very briefly is we're now starting to ask about how these things might affect, for example, ion trap systems like you have here in the lab that I was looking at just a few minutes before the talk. We already talked about ideas with quench dynamics in these systems where you can arrange really long-range interactions, where we see different behavior for short-range interactions and long-range interactions. We want to ask now how scattering, decoherence, and thermalization change in these sorts of systems. So with that, let me thank the different people who worked on this, in particular Johannes Schachenmeier, who did a lot of the calculations on the thermalization, Shavik Sarkar and Stefan Lange, who have been working on the fermionic case, and our external collaborators, Loda Pollitt and Matthias Treuer. So the bottom line take-home message is that dissipative dynamics can be very interesting in these experiments. It's not sufficient to simply estimate the energy that you're putting in when you look at heating in an optical lattice experiment. The dynamics can be much more complicated. They can involve out of equilibrium systems, a lack of thermalization, and it turns out both to be fundamentally interesting and also very important in terms of calculating real heating rates in the experiment. And the nice thing is that if you just calculate the rate of energy increase, you typically will overestimate the amount of real heating that you get. The systems are actually more robust than that when you look at the many-body dynamics. And so at the end, there is a positive practical message for these experiments.